Dad, how did this get here? Didn't we just order it like a few hours ago?
When my older daughter asked that, I stopped for a second because it is a simple question with a surprisingly deep answer. Somewhere between a tap on a screen and a box on our doorstep, invisible systems spin up, data races across networks, decisions get made in milliseconds, and the physical world moves. It's fascinating to think what happens when you stream a song, book a hotel room, reserve a flight, or open an app and just expect it to work. All this technology is so fun, and I love working in this industry. I've spent my career building software and systems that make up the internet. I was CTO at Shopify and ServiceNow, an SVP at Slack, an early engineer at Cisco Systems, and now I'm CTO at Webflow. I've helped build data centers, protocols, software, and services, and led global teams along the way. This podcast is for anyone who wants to understand how our modern world actually works, not just shopping and delivery, but the invisible machinery behind nearly everything we do. It is for anyone who's ever wondered, how did this get here? Or how did that actually happen? I'm excited to take you on a journey, to take these layers of technology apart and explain them in a clear, grounded way. You probably think you connect to Wi-Fi, you're on the internet, and away you go. Well, I wish it was that simple. I'm Alan Meinwand, and welcome to Pixels to Packages. Hello everyone, and welcome back to Pixels to Packages. Back in episode 1, we followed a click on a shopping site as it became packets, moved across networks, and into a data center to finally buy that thing online. In episode 3, we explored a lot of concepts behind this: load balancers, virtual IPs, distributed systems. And in episode 6, we stepped back and looked at routing more broadly, both on the internet and in the physical world and in warehouses. And we saw that moving packets and moving packages are really different versions of the same problem. And I got a lot of requests online to go deeper. So today I want to go deeper into that one question that sits underneath almost everything we've talked about so far. How does the internet actually know where to send traffic? This is so important because everything that you do on the internet depends on routing. It's literally how everything gets from your phone, your laptop, your watch, your camera, anything that's connected to the internet. Anything you type into a browser, every email, every Instagram post, every iMessage, every WhatsApp, every Venmo, every photo, every ChatGPT session, you get it. Everything depends on routing. And people really want to learn some more about that. And because the technology here is so cool, we're going to do that. We're going to dive in deeper. So, when you type Amazon.com into a browser, your computer first has to resolve that name into a numerical IP address. We covered that concept called DNS, or Domain Name System, back in episode 1. And we talked how DNS walks the hierarchy from root servers down to authoritative name servers and returns a precise address in just milliseconds. If you haven't listened to that episode, it's a great place to start because everything in this episode depends on it. And once your system has an IP address, the real question sort of begins. How does your request from your browser, from your laptop, from your phone, find Amazon's infrastructure somewhere out there on the internet? When you send a chat prompt to ChatGPT, how does that traffic cross cities, countries, oceans, data centers, and get an answer? Who decides which path those packets take? The answer is a lot more complicated than most people realize, and something I really enjoy talking about. Because the internet is not just one network. There's no big master map of the internet. That would be pretty impossible. No global traffic controller, no central system that knows where everything is. Instead, the internet is tens of thousands of independently operated networks, exchanging information in real time, reacting to failures, adapting to congestion, negotiating traffic exchange agreements, and making decisions in real time for routing. Billions and billions and billion times a second. Matter of fact, this podcast you're listening to is packets going over the internet, following routing. That's how it gets to you. And somehow, all of that complexity, all of those things that enable that to happen, packets usually arrive exactly where they need to go. So today, we're going to slow that process down a bit and trace how the internet actually finds its way. Now, back in episode 6, we used the analogy of the postal system to explain routing. Packets were like letters, routers were like sorting facilities, networks were like cities or postal regions. Turns out that analogy is really, really accurate. And today we're going to push it even further. So let's think about how physical snail mail works. A letter contains several layers of addressing for getting from point A to point B. It talks about a person or a company name, a street address, a city, a postal code, a country. These different layers of abstraction matter because the postal system routes hierarchically. If you mail a letter internationally, the postal system does not immediately care about the exact house. First, it moves the letter towards the correct country, then towards the correct city, then towards the correct postal code, and eventually toward the local street address and the destination. IP addressing, the internet protocol addressing, works very, very similarly. The internet routes traffic in stages. Packets move towards progressively more specific destinations as they get closer to where they're going. And just like physical mail, traffic doesn't always follow the exact same route. In the physical world, if I take two letters and mail them in the same day to the same destination address from the same post office box, they actually might travel on different sorting facilities, arrive at different times, encounter different delays along the way. On the internet, direct connections to the same destination may traverse different paths along the network, depending on the conditions at any moment. Again, back in episode 1, we talked about something called the Transmission Control Protocol, or TCP. You hear it a lot with TCP/IP, they kind of go together. So TCP is the connection, and IP handles the routing and addressing. TCP handles reliability and sequencing, and we spent a good amount of time talking about how TCP numbers packets, waits for those acknowledgments, and retries lost data. The same machinery is what makes the internet feel solid, even though packets are being routed independently underneath. So TCP is your browser, your phone, your laptop to the destination server behind the load balancer in the data center. It makes sure everything shows up in sequence and retried and reliably. IP is the routing of the individual letters or packets underneath it that can take different routes. So the internet is not one continuous stream. It's millions and millions of individual packets being routed independently and then reassembled at the destination, maybe resequenced by TCP. So again, if you haven't listened to the first 6 episodes, I'd really encourage you to go back and check those out. They lay the groundwork for everything we're about to explore today. You see, every device connected to the internet has an IP address, internet protocol. But an IP address is not just some random number. It is hierarchical, and that hierarchy is what makes global routing possible. Again, you can almost think of it like a mailing address. Part of the address identifies the broad network, which is a little like a country or a region. Part of it identifies the subnet or the subnetwork, which is kind of like a city or a postal code. And the final part identifies the specific device, the actual thing you're sending from, which is like the individual house, the individual mailbox. Each packet carries a destination IP address and a source IP address, and that address encodes all 3 of those in a single number. The network portion identifies the broader group of addresses the destination belongs to. The subnet portion narrows it down to a specific segment within that network, and the full address pinpoints the exact device. So think about the network being maybe your ISP, the subnet being the neighborhood you're in, and the exact address being, your device on your home network, sort of thing. Routers use these layers to make forwarding decisions, and sometimes matching just the network portion, because all you need to know is to go to that region or to that network. Sometimes matching the more specific subnet portion within inside of your ISP, you want to get to your home or your street, and sometimes matching the exact address, because once you're here, you want to know, is it this laptop or that laptop or this phone or that phone, sort of thing. How that actually works is one of the most important things we're going to cover today. Because today the internet runs on 2 different versions of IP addressing, just to be confusing, and the difference between them is pretty dramatic. The first version is called IPv4. IPv4 is the original system. It's been the foundation of the internet since the early 1980s. IPv4 uses 32-bit addresses, which is a block of 32 ones and zeros. That means the total number of addresses there is 2 to the power of 32. That works out to about 4.3 billion addresses. Now, when IPv4 was designed, 4.3 billion seemed like a pretty large number. But as we all know, today there's over 8 billion people on the planet, and most of us have multiple connected devices. Now you add in servers, infrastructure, sensors, cameras, smart appliances, all sorts of stuff that's out there connected to the internet, and 4.3 billion, believe it or not, is nowhere near enough. So IPv4 doesn't even provide one address per every person alive today. And we know a lot of people have more than one device. So the internet ran into this limit a bunch of years ago. We were all sort of panicked about it back in the late 90s, early 2000s. And the reason IPv4 survived this long is because of something called network address translation, or NAT. Now, we touched on this briefly again back in episode 1, and we talked about your home router and how your home router presents all the devices at your house as a single IP address out to the internet. And that single IP address represents all the other IPs in your home. So there's like a public IPv4 address that probably your local ISP device at your house represents out to the internet. And inside of that, you use a private IP address space. This adds some complexity, but it actually allows us to use a private IP address space, which is much bigger, inside of everyone's home or inside of a given network, while only presenting publicly one address. So there's a lot of different ways that we sort of extended the life of IPv4. And when a lot of people talk about IP addressing, this is what they're talking about: a 32-bit number that is presented publicly on the internet. Now, a while back, we also designed something called IPv6. IPv6 was sort of designed to solve this problem permanently. So instead of 32-bit numbers, IPv6 uses 128-bit addresses. And the difference in that number is pretty hard to imagine. So 128-bit means you have 2 to the 128th power numbers. That's approximately 340 trillion addresses. It's 1 followed by 38 zeros. It's a big number. To put that in perspective, astronomers estimate there's roughly a trillion stars in the observable universe. IPv6 could assign approximately 300 trillion unique addresses to every single one of those stars, and still not run out. It's a lot of numbers, like I said. You could assign an IPv6 number to every grain of sand on every beach on every desert on Earth, and you'd only use up a small portion of the address space. So we sort of solved that problem in a big way, and we designed IPv6 so that way we don't have to deal with this network address translation, no matter how many devices each human connects to the internet. Now, whether using IPv4 or IPv6, they both follow the same hierarchical principle, whether it's a 32-bit number or a 128-bit number. They're both routed the same way. Now, what happens is every IP packet, every packet underneath that TCP connection, every packet that every router is looking up, every letter, if you will, that the post office is figuring out how to sort, carries that address. And the routers, like the postal service, doesn't really care what type of address it is. It can read them both. It's like saying your local mailing facility can read multiple languages of an address on a letter. Routers really just care about one thing. From where I'm sitting right now, as I look at this destination IP address, 32 bits, 128 bits, whatever it is, which neighboring router gets the packet closer to where it needs to go? What is the next hop on the path? That's really what every router is doing. That's what the router in your home is doing. That's what the routers to your ISP is doing. That's what the routers at Comcast and AT&T and British Telecom are all doing. And this is what makes the internet inherently scalable. Now, if every router on Earth had a store entry for every single possible address, this would be impossible. Instead, routers sort of reason about groups of addresses. Again, think like countries, regions of a country, postal code, or streets. The entire network or subnetworks are aggregated into what's called prefixes, so that every single routing entry might represent thousands or even millions of individual devices. Again, the analogy of the postal system would be like a zip code represents thousands of houses or tens of thousands of houses. There's a technique, what's called CIDR, or classless interdomain routing. It's one of the key engineering decisions that allow the internet to scale from connected networks of thousands and thousands of connected networks to be able to scale and route to the internet that we've seen today. So this idea about classless interdomain routing, or CIDR blocks, is the ability to actually look at the aggregate portion of the address and only route on the portion that's really relevant at that time. Now, if you're inside of a large organization, they further divide their infrastructure into smaller pieces of a network called a subnet. And this is sort of how like cities divide into districts. And that subdivision, again, makes routing more manageable. You don't need to know how to go to every address within the Mission District of San Francisco if you're outside of San Francisco. You just need to go to San Francisco, and then the routers in San Francisco or the postal carriers in San Francisco need to know how to go to the Mission District. So just like every letter, every packet carries a destination IP address. And that IP address encodes all those layers. The network portion identifies the broad group of addresses, the subnet portion narrows it down to a specific segment, and the full address pinpoints the exact device. Routers use these layers to make forwarding decisions, and depending on how far away they are, these forwarding decisions get more and more exact. They really only need to know enough information to move the packet one step closer to the destination. And as you get closer and closer and closer, the routers that sit closer to your device know the very specific information. Now, how that lookup actually works is another really important thing we're going to cover today. You see, no single router has a complete picture of the entire internet. We've said that that's impossible. Routers only need to know how to make the next decision. So a router receives a packet, and it opens it up and it looks at the destination IP address. It then performs a lookup into something called a routing table. Think of a routing table as the reference guide that tells the router where to send the traffic next. It's the heart of every router. It's the thing that every router tries to build, is a routing table. You can sort of think of it like a sorting guide at a postal facility. Each entry in the guide says, mail headed for this region, put it on this truck. Mail headed for this other region, put it on that other truck on loading dock 3. A routing table works the same way. Each entry in the routing table contains a few key pieces of information. First, the destination. Where is this going? Which is a network prefix representing a range of addresses. That prefix might be a broad network, which we're going to talk about in a little bit. It might be a subnet portion of that, or it might be a very specific address, very, very local to where that router sits. The next thing that's in the routing table, if you think about them as rows in a table, it's destination IP address. The next one is the next hop. The next hop is the IP address of the neighboring router. Where do I send this to next? The third is the outgoing link. Which connection do I use? Remember, routers are interconnected by satellite and fiber and copper. And these routers, as we'll hear about in a bit, sort of communicate over which networks are available over each of those paths. So this particular network to this next router over this type of circuit is what's next. And the fourth metric is what's called the cost. And that describes how desirable that path is. You can imagine that you have multiple ways to get to a different destination, and you have to make a decision. And the cost is what allows you to make the decision between route A and route B. Now, when a router looks up a destination IP address, it searches for the most specific matching entry. Think of it like this. If your postal sorting facility might have a general bin for all of a given state like Illinois, and a more specific bin for Springfield, Illinois, because we're in Springfield in this example. A letter addressed to Springfield matches both. It says I'm in the state of Illinois and I'm going to the subnet or the city of Springfield. Now, routers work the same way. If the routing table has a broad entry for a large network, this is going to France, this is going to AT&T, and a more specific entry for a specific part, it's going to this particular portion of AT&T. The more specific entry wins. This is how the hierarchical addressing we talked about earlier pays off. Routers can have general routes, and then they have more specific routes. And if you encounter a router and the router looks at the destination IP address, the more specific routes work. This lookup, this fundamental longest match, it's called, or more specific route match wins, is a fundamental operation of routing. Every router on every hop performs the exact same sequence. Examine the destination IP address. Find the best match, the longest match in the routing table, and send the packet out the corresponding link to the next router along the path. And that occurs hop by hop by hop, router by router by router, satellite connection, fiber connection, copper connection, until the packet reaches the destination network and is finally delivered to the specific device. The route is to the exact device itself, and it's local. Again, this is called next hop routing, and it's a little like navigating through the city one intersection at a time. At every intersection, you don't need to know the entire route. You actually don't even care where you came from. You just need a sign that tells you which road to take next. Now, if you want to dig in a little bit more, as if this isn't enough, you can look at your routing table. If you're on a Windows box, you can type route print. If you're on a Linux box, you can use IP route show. If you're on other Linux versions like Mac OS, you can type netstat-r. All these are in terminal commands. These are terminal commands. You can go in. You can actually see the routing table. Destination, next hop, cost. You'll see it all in there. Now, the routing table doesn't just magically appear. It doesn't populate by itself. Routers learn these routes through routing protocols. Some of the coolest things I've ever worked on, which are systems that automatically discover network topology and share reachability information between routers. Different routing protocols handle different types of routes and different types of scopes. Inside a single organization or a single provider's network, there's something called an interior routing protocol that populates the routing table with routes internal to that network. When you get between organizations, we have an entirely different protocol. It's called an exterior gateway protocol, and the one here is called BGP, or the border gateway protocol, that populates routes to external networks, larger groups across the internet. So now we're going to go a little bit deeper and cover those in detail. And I'm going to start with interior routing and interior gateway protocols. So an interior gateway protocol called IGP. We got a lot of acronyms in networking, just kind of get used to it. An interior gateway protocol, IGP, is a routing protocol used inside of a single autonomous system. We touched briefly on autonomous systems in episode 6 when we compared the internet routing to the postal system back then. So an autonomous system is an independently operated collection of networks under a common administrative control. It's an organization. An ISP is an autonomous system. So is a cloud provider like Amazon. So is Shopify. So is university or a large enterprise. Inside of that environment, routers really work closely together. Inside of an AS, inside of an autonomous system, the routers really want to know how to get to those specific addresses. Because once you get into that local postal code or into that local town or into that local district of a town, you want to know everything. So they exchange information about the links that are between them. All these routers are exchanging information. So picture like this big graph of all these links that are connected. And they exchange information about the cost of going through those links. Cost here does not necessarily mean money. It most often represents latency or bandwidth or speed, or maybe even operational preference. Like I prefer to take this route versus another route. A high-speed fiber backbone might have a lower cost than a slower congested copper link. A direct path between two locations might be preferred over an indirect one that hops through multiple of the routers. Sometimes not. But the goal is straightforward. Determine the best internal path, the interior path, for any packets at any given moment within that organization's network. The routes that an IGP discovered get installed into each router's routing table. These entries map internal destinations and subnets to the specific next hop routers and their outgoing links. This is where the hierarchy of IP addressing that we talked about earlier comes into play. An IGP might install a broad route for an entire network, but more specific routes for particular subnets within that network. When a router inside an organization receives a packet for a destination inside of its own network, it performs that same routing table lookup we just described. Destination, next hop, cost, outbound link, and it finds the most specific match, the longest match. And generally, that's very specific inside of the autonomous system. And it forwards the packet out to the next router on the way to the destination. So over time, two fundamentally different approaches to these internal routing protocols emerged. There's like an older school way called distance vector and a new modern way called link state. So I'm going to briefly describe the algorithms of the interior gateway protocols, the IGPs. So historically, one of the early routing protocol models, if you will, the algorithms, was called distance vector routing. And the idea was really simple. Every router within inside the network would essentially ask its neighbors, how far away from this destination and which are you? And which destination, which way should I send the traffic? So every router learned three basic things about the destination from its neighbors. What the destination was, whether they get there or not, how far away it was, and which neighboring router to forward the traffic to. The shortest path, the way to get there, was generally measured in hops. So if router A was connected to router B was connected to C, and A was also connected to C, then any traffic from A to C, or to more specifically to networks connected to C, would go A to C as opposed to A to B to C. So it's a little like standing at an intersection and asking people on all of the nearby roads which direction downtown is. You really only need to learn the next step, and you pick the one that's the shortest. You have no idea what the full map of the city looks like, but you just know that if I take that street, it's only 2 intersections. If I take another street, it's 4 or 5. So there's a protocol that stands for RIP, it stands for Routing Information Protocol, it worked this way. And for small networks, it worked just fine. But the problem was we had this convergence problem. You might remember in a previous episode, we talked about convergence. And the problem with distance vector protocols is, remember, you're learning about things from your neighbor, and they learn it from their neighbor, and they learn it from their neighbor, and they learn it from their neighbor. So if things out on the network start to change, and networks are always changing all the time, then they had limited visibility, and they had to wait for that information to sort of ripple back to them. So I might think that the path from A to C is the most direct path, and I might think that A to B to C is the most indirect path. But it turns out that C might not actually have a route to the network I'm trying to go to anymore, just hasn't told me in a while. And now I'm sending traffic down a path that isn't viable anymore. So this limited visibility worked for very, very small networks, 3 nodes, 4 nodes, 10 nodes, 100 nodes. But as you start to get bigger networks with larger complex topologies, it really created lots of problems with routing loops and outages, and really the idea of convergence. When something changed on the network, this hop by hop by hop propagation of information was too slow. And as networks grew to be larger, more dynamic, we needed something a little more sophisticated. So modern interior routing protocols, IGPs, evolved a fundamentally different approach called link state routing. This is how everything that you've ever routed on today, every packet that you've ever sent in the past 10 years works. So instead of only learning about the destinations from its neighbor routers, every router in a link state routing protocol builds a complete topology map of its own network in its own memory. Every router floods information about its directly connected links in directly connected networks to every other router in the network. Once every router has the same picture, each one independently computes the best path to every destination using an algorithm called the shortest path first algorithm. So real basics. Every router looks at which networks it's connected to, which networks and subnets it's connected to, and announces to every other router, in a bit of a hierarchical approach, but announces to every other router, here's what I can get to. Every other router on the network picks all that information up, puts it together into a tree, and builds this link state database tree. And then it runs what's called the shortest path first algorithm to figure out from where it sits today, what is the shortest path based upon cost to get to every destination. And that shortest path fills in the routing destination, the next hop, the cost, and the router. You might have just heard me slip up there a second ago. I almost said open shortest path first. Well, it turns out that OSPF is the most popular version of the shortest path first algorithm. and it's probably one of the more popular IGPs in use today. So you hear a lot of us talk about OSPF. It kind of rolls off the tongue instead of just shortest path first. So the best way to think about OSPF or another link state protocol called ISIS, intermediate system to intermediate system, again, lots of algorithms, lots of acronyms. The best way to think about this is every router has a real-time GPS of the entire city or the entire network. Every road, every connection, which paths are fast, which ones are flowing, which ones aren't flowing, which intersections are congested, is there any infrastructure that's failed, all visible, all updated in near real time. So we talked about how this works. Protocols talk, routers build that link state database. That link state database in turn is interpreted and you run the shortest path first algorithm and you generate the routing table. Remember, whether you're using distance vector, whether you're using link state, the goal is a routing table. You want a router to be able to pick up a packet, look at a destination address, find the longest match, go through the routing table, say, where do I send this? Is it going to router A, B, C, D? What's the cost? And what's the link? What's the thing I need to go put it on? Put it on this piece of fiber, put it on this piece of copper, put it out over this radio network. So all that is what's happening in real time with routing protocols and with inside of IGPs on every router on the planet. It's, again, really so cool. Now, we've been sort of talking about networks as if they're static, but they're not, of course. Fibers get cut, routers reboot, power systems fail, traffic spikes, entire networks shift, new networks are brought up, old networks are taken down, and routing systems have to adapt constantly. This is a process called convergence. When something changes in the network, whether a link fails or a new path appears or cost changes, routers need to learn about that change. They need to recompute their paths, and that recomputing of those paths, that converging of paths, builds a new routing table. Remember, the goal here is always to get to a new routing table. And speed for this convergence matters a ton. The faster you can converge, the better. If convergence is slow, those millions and billions of packets you're routing a second, they just get dropped. Routing loops can form, things called black holes can happen, applications can fail. We've all seen a website that wasn't available, probably because of a routing issue. It's sort of like imagining a major bridge in a city suddenly gets closed during rush hour. All the traffic systems need to reroute, the buses need to change, people need to hop on trains or something else, and we need to figure out how to manage that congestion. So modern link state protocols are optimized for incredibly fast convergence. Failures can be detected and routed in milliseconds to seconds, depending on the size of the network. They do have the speed of light thing to deal with, but other than that, you can go really, really fast. Most users never even notice when these convergences happen, because it's happening every second of every day underneath all the networks out there. And this is one of the reasons that the shift from distance vector to link state really mattered so much. When a link failed in distance vector, the news travels slowly from neighbor to neighbor. In link state, every router hears about the failure almost immediately and computes that link state database, which in turn builds a new routing table independently. So you have a sort of a scalable, distributed systems approach as opposed to a sharing of messages approach in distance vector. The result is dramatically faster and up-to-date routing tables across the entire network. So distance vector, link state, two routing protocols, or two routing protocol algorithms really designed to react to changes and build routing tables for a given router. So everything we've talked about so far, interior routing, link state, routing table lookups, all that happens inside of a single network. But as I'm sure you know, the internet is not one big network. It is a federation of tens of thousands of independently operated networks, and those networks are each an autonomous system. Comcast is an autonomous system, so is AT&T and Google and AWS and Cloudflare and Deutsche Telekom and NTT and Singtel. Universities operate autonomous systems. Governments operate autonomous systems. Large companies operate autonomous systems. They're all operating their own network with their own interior gateway protocol, with their own routing algorithms to figure out how to get the best traffic routing within inside of their network to their networks, their subnets, and their specific addresses. They have their own operational policies as well. And people running these networks figure out how to best populate the routing tables and make their routers do the things for them. But between autonomous systems, between organizations, routing becomes just a bit more complicated. Because now you have to throw in economics and business arrangements and performance and sort of like policy all enter the picture. And this is where the internet starts to look a little like an engineering and an algorithm and more like international diplomacy. Really. So the protocol that allows that diplomacy is something that connects autonomous systems, and it's called BGP, or the Border Gateway Protocol. BGP works entirely differently than the interior routing protocols that we talked about. It's not like OSPF. It doesn't use the shortest path first. It's not disinfector or link state. It uses something different. Now, interior routing protocols use topology maps. Remember, every router inside of a network sees the links, the cost, the path, and uses that information to compute the routing tables for specific subnets, specific networks, specific addresses. BGP doesn't do that. BGP tracks reachability. It's a reachability protocol, and it tracks it at a much higher level. The distinction is really important. BGP routers don't attempt to map the entire internal structure of every network on the internet. Impossible. Instead, BGP tracks which destination networks are reachable through which neighboring autonomous systems. That's important. We'll get back to that in a little bit more. It advertises that reachability using two things: a network prefix, a portion of the network, and the autonomous system number. So it basically announces something called the autonomous system number and an AS path. An AS path is sort of like, in order to get to this region of the world, what other portions of the world will I have to go through without knowing the inside of each of those regions. So for example, if your network needs to reach a network in Japan, and there's two possible routes, one through a single neighboring autonomous system and another through three intermediate systems. BGP records both those paths. An AS path of 3 hops tell you the network would traverse 3 independent individual networks, 3 clouds, if you will, to reach the destination. An AS path of 1 hop means that it's directly connected. I can get to Japan directly. Again, you can sort of think of this as like countries exchanging information on border crossings. France does not need the internal street map of Japan. It only needs to know which neighboring countries can help route mail from France to Japan, and how many borders that traffic would need to cross. So BGP populates routing tables just like interior gateway protocols do. So the routing table still has routes in it. It's still route, cost, next hop, and the link to go to. But the entries inside the routing table look fundamentally different. A BGP routing table maps a destination to an AS path and a next hop router and the next hop connection, the fiber, the copper, the satellite link, whatever. But what's missing is there's no individual subnets, no individual host IP addresses. The subportions of the network are gone. All you get is, again, using the postal analogy, the country code, the big blob. BGP operates at this network level. Its job is to get the packet to the right autonomous system. Once the packet gets picked up by a router inside of that autonomous system, then the longest match algorithm takes over, and you start to follow the routes set up by the IGP, by OSPF or IST-IS. So once the packet reaches a network that contains its final destination, the interior routing protocol takes over, used a more specific routes in the routing table to forward the packet to the correct subnets and then to the correct device. Similarly, when a border router at the edge of an autonomous system receives a packet destined for an external network, something it doesn't know anything about, it doesn't have a longest match for, it performs a routing table lookup just like every other router. But the matching entry is a BGP learned route. And that entry tells the router which neighboring autonomous system to forward the packets to, and which link and what's the next hop. The packet goes out that link, crosses the border, and the neighboring router does the exact same thing. It says, do I need to pass this to another network, to another autonomous system, or is it something for me? And I pass it into my IGP, my interior routing protocol, to look up the network and the subnet and continue to route it. So this separation of concerns is fundamental to how the internet scales. BGP handles inter-network reachability using autonomous system numbers, network prefixes, and AS paths, autonomous system paths. IGPs handle the interior network using network, subnet, specific addresses, etc. But the common thread is the decision-making tool that the router uses, and that's the routing table. But here's the critical thing about BGP. Once traffic enters an autonomous system, you sort of lose all that visibility. The GPS goes black, if you will. So if you're in France and you know you can go through the US to go to Japan, or if you're in France and you know you have a direct link to Japan, once you hand the traffic off, once BGP says from France to Japan and hands it to Japan, you don't know what happens inside the network. It could be slow. It could be super fast. The traffic could be paused for days, hours, weeks, probably not, but you know what I mean, sort of an analogous to mail. Every autonomous system is essentially opaque outside of that autonomous system to the rest of the world. Again, let me make this concrete with an example. Again, imagine France is connected to Japan. France is also connected to the US, and the US is connected to Japan. So the United States advertises to France via BGP that it can reach Japan. Japan advertises to the US, it can also reach France. Now, France has multiple choices for traffic destined to Japan. It can send traffic over its direct connection to Japan, or it can send traffic to the US, and the US can forward it. The direct path of an AS path length of 1 generally is better than an AS path length of 2, 3, or 4. But the path to the US might actually be better. You can't assume the shortest path always wins, because this is what gets internet routing even more fascinating. Yeah, it keeps getting more and more fun, doesn't it? See, routing on the internet isn't just an engineering problem, it's also an economic problem. Networks make routing decisions based on cost, performance, congestion, reliability, business, money, and operational goals. A direct path actually might be more expensive. It might be congested. It might rely on an expensive undersea cable. A longer path through a different provider or a different country or a different network might actually be cheaper, faster, or operate more reliably. So this process of figuring out, even though I have two different AS path lengths between two different networks, figuring out which one I actually want to use is called traffic engineering. And it really shapes how an enormous portion of the internet actually routes. Sometimes traffic between nearby geographies takes surprisingly indirect paths because those paths are not economically or operationally better. The internet optimizes for many things simultaneously, not just distance or hop count or necessarily speed. We touched on this back in episode 6, when we compared BGP routing to international trade agreements rather than GPS navigation. And today I want to take that a little further and explain two different types of business relationships that underlie it all. The first is called peering. Two networks agree to exchange traffic with each other, usually at no cost to either side. So peering works well when both networks roughly have the same amount of traffic, roughly have the same economics, and they benefit from each other. Peering connections happen at places called Internet Exchange Points, or IXPs, peering points. And they're physical facilities where hundreds of these networks come together and they sort of agree to share information, share BGP routes, and freely exchange traffic. The world's largest internet exchange points handle terabits of traffic a second. You've heard of these. There's the London Internet Exchange. There's the Amsterdam IX. You hear about these exchanges all the time. There's a big one in Ashburn, Virginia. There's some in the West Coast. They're large internet exchanges where people come together and they peer and they exchange BGP routes. They exchange autonomous system paths, and they agree to sort of pass traffic to each other. Now, the second type of relationship is called transit. And in a transit network, you have a smaller network paying a larger network to carry its traffic. Transit providers are essentially selling reachability via BGP. So if you're a small ISP and you can only afford connections to a couple of networks, you buy transit from a large provider and they can get you everywhere. So if you're a small corporation or an enterprise of some sort, and you don't worry about all this BGP stuff, and you don't want to set up peering, and you don't want to set up connections to all these places on the planet, you connect up to AT&T, you connect up to British Telecom, you connect up to, Singtel, and you say, you're my transit provider, I'll pay you this much per month or this much per year, send you my traffic, and away it goes. So these types of relationships, peering, where people share routes, and transit, where you buy routes from people, sort of create these different layers of economic structure that really influences a lot of routing decisions across the entire internet. Part of those routing decisions have to deal with something called hot potato and cold potato. We all like potatoes, but these terms are some of the more memorable ones in networking. Hot potato routing means get the traffic off my network as fast as possible. So what you do is you hand it to your network provider at the nearest internet connection point, even if there's a longer path or even if there's a shorter path. Hot potato routing says, yes, Mr. Customer, I'll take your traffic, but I'm going to get it off my network as fast as possible. I don't care if it's a 15 hop AS path length from here, I'm just going to get off. And why would I do that? Because carrying traffic on your network consumes capacity and cost. And the sooner you hand it off, usually the less you spend to carry that traffic. So if I'm a transit provider, I might provide the entire internet's worth of routes. I might provide a full BGP table down to an enterprise customer. But as soon as they give it to me, as soon as they give their traffic to me, and I look up that destination IP address in my routing table, I'm going to hand it to any other network on the planet that I'm connected to that can handle that traffic as fast as possible. Now, cold potato routing is the opposite. This is when a network intentionally keeps traffic on its network as long as possible. It's trying not to hand it off. And you might ask yourself, why would it do that? Well, it's because it has more control. These are generally network providers that want to provide a better experience, provide high reliability, provide better end user experience. Large cloud providers and CDNs often offer cold potato routing because they operate really high quality global backbones, and they want to keep that traffic on their own network so their customers will have a better experience. When Google or Amazon carries your traffic across their own fiber, before they hand it off to some random ISP that happened to advertise a BGP route to them, they can guarantee the level of performance they can't. Remember, once you take the traffic off your autonomous system and hand it to someone else, you have no idea how it's routed. Once Japan gives the mail to the United States, it doesn't know if the United States keeps it in a sorting facility for hours, minutes, weeks, months before it hands it off to Japan. So what you want to be able to do is think about, how does the protocol react? How does the protocol want to handle traffic, whether it's hot potato or cold potato? And what's the quality of the network that you're thinking about when you're making these connections? Because hot potato and cold potato are not just theoretical concepts, although they're fun to say. They represent real economic and operational trade-offs that network engineers negotiate constantly. There's humans setting all this up. There's humans that say, when this packet shows up for this destination network, regardless of AS path, send it this way. Somebody configures that. And that's one of the reasons that the same traffic can take very different paths on any given moment, on any given day, between destination A and destination B. Think about all the things we've talked about, right? We're trying to say, going from a browser, hitting a buy button, going to a ChatGPT session. That's a TCP connection with the sequencing numbers. Underneath that, you're routing locally. You're through an IGP. You're doing link state. You're going across multiple autonomous systems. You're dealing with BGP. Your traffic is being traffic engineered. All that before you ever reach the destination data center, the destination load balancer, the destination web server, the box model, all the things we've talked about. All of this happens when you hit click and that web page shows up, or that iMessage shows up, or that podcast hits your device you're listening on. It's all happening in real time so quickly. So let's zoom out one more time here. There are 70,000, roughly, active autonomous systems on the global internet today. Probably growing. Probably by the time this podcast gets out, it'll be more. As we mentioned back in episode 6, the BGP global routing table contains over 1 million prefixes and continues to grow. When you got 1 million prefixes, 1 million different destinations in that routing table, things are changing all the time. Links fail and recover, new networks appear, traffic pattern shifts throughout the day as people wake up and go to sleep. Every second, routers across the planet are processing BGP tables, recomputing internal paths, recomputing the link state database, building new routing tables, and making forwarding decisions for billions and billions of packets. And all of it seems to work remarkably well. I honestly think it's one of the great engineering achievements of modern technology. I really do. It's the core basis of everything. And not because it is like centrally controlled, but because this is a decentralized, adaptive, cooperative, competitive, and constantly evolving distributed system. No single organization designed the internet as it exists today. Nobody controls it. It's emerged from decades of independent decisions made by thousands of operators, all following these protocols we've been spending our time talking about so far in this series. So let me bring this all the way back to the browser on your screen. Every time you click a link, your system resolves to a domain name into an IP address using DNS. Your data then becomes packets. Those packets carry hierarchical addresses, IPv4, IPv6. That encodes the destination network, the subnet, and the specific device. At each hop along the way, a router examines the destination address, looks it up in its routing table, finds the most specific matching entry, forwards the packet out the right link to the next hop router. And the next hop router does the same thing, again and again, until that packet gets to the destination. And the next hop is your device. Inside each network, interior routing protocols compute the best internal paths and populate routing tables with routes to specific subnets and addresses. Between networks, BGP exchanges reachability information using autonomous system numbers and network prefixes, so tens of thousands of independently operated autonomous systems find each other and communicate together. AS paths are computed, recomputed every second of every day. Humans are doing traffic engineering to shape the way that traffic works. Economics and policy influences that just as much as the algorithms and the technology does. Peering and transit arrangements are being negotiated right now, and they determine who carries traffic and for how long. Hot potato and cold potato strategies determine when traffic gets routed, when those packets go from network A to network B. And underneath every web page, every video stream, every shopping transaction, every AI prompt, packets are negotiating a constantly shipping web of independently operated infrastructure, forwarded one hop at a time by routers that know just enough to make the next decision in their routing table. The internet is not one machine. It is thousands of networks continuously cooperating and competing at the same time. And somehow, miraculously, from all that complexity emerges something that feels almost instantaneous. Back to what my daughter asked, how did this get here so quickly? Well, routing's underneath it, and routing made it all happen. That's routing. And honestly, after spending so many years building the systems, I still think it is just magic. It's the basis for everything on the internet works globally. And having the knowledge, just a little bit of knowledge that you have now, the in-depth knowledge we talked about today, is going to be so important, especially in today's interconnected world. So I'm Al Manwand, and thank you for joining me for episode 7 of Pixels to Packages. If you've been enjoying the series, go back and listen to the early episodes if you haven't already. And please subscribe, share the podcast with a friend who might find it interesting. Remember, every episode builds on the last, so the deeper you go, the more you start seeing these hidden systems that are everywhere in our world. Thanks again.